This UCSD TV program is a presentation of University of California Television for educational and non-commercial use only.
Good evening. I'm Ken Searcy from the San Diego Astronomy Association. So what they asked me to do was to give you some information on the sorts of things that the amateur astronomy community can do for the education community. So what I'm going to show you is not really standards-based material, right? Because I know you get plenty of that, but it's material that we tend to use, or I tend to use, with kids about your ages, 4th grade to 9th grade, and it's really based more on the Girl Scout and the Boy Scout material. They're pretty astute about figuring out age-appropriate things for these kids, and by experience, when I go out and do some of these demonstrations that we'll do, the kids don't really know it. Even 9th graders and 10th graders are a little foggy. So it's very relevant to the age group. I don't know exactly how relevant and how useful some of the things are within the curriculum environment. Tonight's outline, I'm going to start with some kind of astronomy factoids, and some are probably news, and some of the others are things that I would do with students. If I were coming to the classroom or around a scout campfire or something like that, the sort of little questions you can ask them to see how much they know. Talk about amateur telescopes largely. What can we see at your school if we came to the school? You know, what would it be like? I'll talk about science fair projects a little bit because we do sponsor a science fair award at the Greater San Diego Science and Engineering Fair. And then some demonstrations, and then there's some freeware astronomy software. There is some nice freeware material out there. Okay, some of the factoids. You know, there is water on the moon and Mars. There is, in fact, water in some of those craters that are along the poles and in the shadows. So there is water, which is very interesting. Maybe not so much for life, but maybe in case our astronauts need water if we want to leave people up there. Just to get water up to the space station, it's something like $100,000 a gallon. Okay, so water, ferrying water around the solar system is kind of a big deal. Mars, of course, has a lot of water. You've seen the ice caps that have some frozen water and some frozen carbon dioxide, but there is a lot of water at mid-latitudes underneath the surface, and they found that with radar. So yes, in fact, there's a lot of water up there. This is something I do with the kids all the time because they get tired of saying, "Why is the sky blue?" And you really do get tired of that. So what I do is, especially if we're out at night, and with the dust and so forth in the atmosphere, this green laser would look like a lightsaber. So why does your laser pointer look like a lightsaber? Is because the molecules in the air and dust particles scatter these frequencies of light. And if I had a red pointer and it were outside, it wouldn't scatter the red. So now, of course, that gets back to why the sky is blue, because it's the blue light from the sun that gets scattered most, and that gives us the blue appearance of the sky. If you're up on the moon that doesn't really have an atmosphere, the sky is black, as it should be. And if it had some other chemical composition, it'd probably be a different color. Think about another one that you can relate to. When the sun goes down and it's at the horizon, it's going to be sort of a brilliant red-orange. Well, why is that? Same reason. What's really happening is all of this atmosphere and dust and so forth has scattered all the blue colors, the blues and greens and so forth, and there's nothing left but the red. When you look out toward the horizon, you're looking at pretty close to 2 air masses versus directly overhead when you're looking at one. So that's why the sky is blue, why the sun turns the color it does at the horizon. Okay. We all know constellations. I've noticed that school kids tend not to realize that the stars in a constellation really don't necessarily have anything to do with one another. So it is a good question. The stars are all moving with their own proper motion. But the stars in the constellation, they're all moving independently of that constellation shape. So if you go forward 10,000 years or so, or 20,000 years, the Big Dipper is going to flatten out, and the stars in the constellations would move. And so people will probably have to come up with newer names. Not that they always look like what they say they are anyway. Groups of stars. Half the stars that we see are really multiple star systems. The majority binary, but they can be 3-star systems, 4-star systems, and so forth. So it's always a good kind of a segue with them to say, what do you call a group of stars? And they'll scratch their heads and so forth, and they're not going to come up with the binary stars and higher systems. The next level up with kind of this homegrown scheme is clusters. And there are 2 general types of clusters that you can see easily, and they are open clusters, it's kind of obvious, which are young, bright stars, pretty much in the plane of the galaxy. And the opposite of open isn't closed, it's globular. And they're very old star populations, very large, thousands to millions of stars, and they're above and below the plane, the flat plane of the galaxy. And they look like a big ball of stars. So an open cluster that you're used to seeing is, of course, the Pleiades, or some other, the Beehive, the Owl, and so forth. The globs are going to look like a real tight ball, almost like a cloud, if you didn't have a telescope. Of course, up from there, of course, galaxies, then groups of galaxies and supergroups and so forth. Star names, catalogs, and the Messier thing. Most of the stars, most of the named bright stars that we have have Arabic names. A few Latin names, more Latin names in the constellations and so forth. But you're really going to see Betelgeuse, Rigel, Deneb, and on and on and on, Rasselhaig. So most of them were named by the Arab astronomers, and those names have stuck. In general, if you're using software or catalogs and so forth, they're all going to have catalog names, and they're going to be specific to the catalog that's in use. But the other thing is the Messier thing, and you notice that we almost use that as a language because we know it so well. Messier was a comet hunter in France about the time of the French Revolution. So what Messier did was, with a smaller telescope than this one, he cataloged the things that looked like that, fuzzy, kind of indistinct kinds of things that never moved and therefore weren't comets. So that catalog, with some additions, and there are a few errors, is become kind of the lingua franca that amateur astronomers use. So that's the Messier thing, and of course I'll keep referring to everything by Messier numbers just out of that convention. So Messier was trying to throw out things that weren't what he was looking for, and he created the catalog of things that we really like. A little bit about telescopes. And I'm sort of doing this from a student's perspective. They always say a telescope lets you magnify things or see things that are distant. And of course that's true, but that's not really what they do. They really gather as much light as you can possibly gather, bring the light down to some area where we can either observe it and put an instrument in its field. So on the left, of course, is the Hale telescope at Palomar, which is a reflector-type telescope. It has this large 200-inch mirror, At one end, the light comes in here, bounces off the mirror, bounces up to the prime focus. You can put an instrument prime focus, or you could be an observer in the early days and sit up there all night with a glass photographic plate. They didn't really use this for visual observations ever. Or else you can bounce the light through a mirror and put, you can see this sort of a cage affair, not particularly well, but there's a cage with instruments, so you can put even larger instruments there. So that's how a telescope that uses mirrors works. And of course, this is your old-fashioned, not old-fashioned, but a classic refractor. So the refractor works almost the opposite. You want to gather light, it comes in, and there'll be an objective lens, or probably a double one, brings the light all the way through. There might be some other lensing here, and to an eyepiece, so you look straight through. So the light, instead of being bent by a paraboloid shape and focused up here at prime focus, it's refracted through the optic, so it actually has to pass through the glass. What could we see at your school? Yeah, stars, and it's more interested if they're double. The stars have colors that are dependent on their temperature. So there is a bright double star, and one component is a nice yellow, and the other's kind of a charger, kind of a blue-green. Yeah, they always like to call that the charger star. So we can go split double stars, and there's a famous set of doubles that are an easy split, but each one of those doubles splits again, so it's really a four-star system. So they call it the double-double, and that's kind of neat. So it's kind of neat to split double stars or clusters. We'll come and look at a lot of open clusters. Open clusters are wonderful. Globs are almost even better. The moon, of course, I said, and I've got a slide on the moon. Planets and their moons. The only moons you're going to see on a telescope this size really are the 4 bright moons of Jupiter. And I'll talk about that. You can see some of the moons of Saturn as well, certainly Titan. But planets are always fun, and I'll talk about planets. Nebula. Nebula, of course, and this is the great nebula in Orion, they're big clouds of hydrogen gas, huge clouds of hydrogen gas, generally star-forming regions. So stars are made of hydrogen, and they burn by fusing. And the kids don't know this, by the way. They all know that they're burning gases and so forth, but it's fusion. It's hydrogen fusing into helium and other components that are the energy source for stars. So since stars are made of hydrogen, almost exclusively, they form in these large clouds, these nurseries, stellar nurseries, if you will. But they're fun to look at. So that's your typical comet, and it is a nice little shot of one with the typical tail that's going. And of course, everybody knows that comets are like a dirty snowball. They're coming outside, way out of the outer reaches of the solar system, coming in, following Kepler's laws and so forth. And when they get close to the sun, then the pressure and the energy from the solar wind cause them to heat up and begin outgassing. And they typically have two tails, a dust and water tail and an ion tail. And sometimes you can see them. Most of the times you can't. But comets are always a big deal at school star parties. So that gives you a little bit of an idea. The planets are always good things. They always want to see Mars. If Mars is up, where can you see Mars? I want to see Mars, 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 Mars. If Saturn's up, Saturn's a pretty neat deal. Clearly, you can see the rings of Saturn through a telescope like this very easily. And everyone's awed. If you've never seen the rings of Saturn, you just have to see them. Jupiter, of course, is my favorite. But really what you can see on Jupiter is you can see the cloud features and the 4 bright moons. You can see them in an amateur telescope very easily, particularly the equatorial belts. And sometimes you see a lot more. The other cool thing about it is that you can see the 4 bright moons. And They're the same ones that Galileo saw with his little telescope, clearly smaller than this, with terrible optics. But nonetheless, he saw those 4 bright moons. They're pretty spectacular. They're going to love the moon. Of course, these are called oceans, or mare for sea. They're really lava plains. There were large cracks, and some of these large basins filled up with lava. So you see this dark lava formation that kind of makes the man on the moon phenomenon that they're used to. But if you look at them with a telescope, you can see the ridges, the riffles, collapsed lava tubes, and so forth. And then other asteroid impacts. On top of that, the cool thing with an amateur telescope is to look beyond, they call this line the terminator, that's making the shadow. So this is pretty neat to see. And of course, you see a lot more detail along the terminator with the shadows and so forth. Let me say a little bit about science fair projects. I don't know how much you push science fair projects in the classroom. Certainly 7th, 8th, 9th graders and above are more applicable, and they can handle the material better. The SDA does have awards for astronomy at the Greater San Diego Science and Engineering Fair. The criteria that we would use: applicability to astronomy, some kind of scientific quality as appropriate to age and talent. So we kind of look for little bit of rigor, but we've got a sense of what's age appropriate. And the one thing you really like to see, and you probably like to see it in the classroom too, is you like to see some analytical ability. It's like, yeah, you did all this stuff, and you got this data, and you got these charts. I know you don't know how to do all the statistical correlations and the tests and so forth, but at least have a good analytical understanding of what you demonstrated. And even better, why? But nonetheless, that's the discriminator. We see a lot of correlations. One last year was, scientifically it's not so good, correlate the moon phases with earthquakes. Are there more earthquakes on a full moon night? There's a popular rumor to that effect, apparently. And of course, that couldn't be true. But nonetheless, this person did an extremely good job, got earthquake tables, years and years and years, built charts, built tables, figured out the phase of the moon and so forth, did a correlation, more of a visual correlation rather than a statistical one. But nonetheless, they found out that it didn't correlate. But it was pretty good analysis, and that was an 8th grader. Light pollution is a good thing. Of course, we like light pollution studies, but it's easier for them to do. And so typically what people would do is they'd go to different locations, different distances from the city, go to the desert, go to Anza Borrego, go midway out, do it at the school or somewhere where it's bright, pick 3 or 4 locations, different times, take pictures, so forth, and come up with conclusions. The conclusion is going to be obvious when you get further away from the light ball of the city and get into certain zones that are protected from the light. It's going to be darker, right? But it is kind of an interesting thing, and you can also do it as a function of altitude too. So there are light pollution, a reasonably well done light pollution studies. Just one of the things we like. Observational projects, I said, they'd need help. They're either going to have to be independent, have enough money to rent telescope time, have their own telescope. There are some schools that have supported things like this. But that's a little bit rare. There is a book, if you want to win it, The Sky is Your Laboratory. There are a lot of neat things that he has in there. Again, it's pretty advanced. But nonetheless, that's kind of the whole notion of science fair projects. Now, actually, what I'm going to do next is a few kind of hands-on demonstrations. One thing you can do, And I've done this at schools, and I built this model in Excel, and we have it with the view graph, so you can use it yourselves. If you Google solar system scale model, you'll see a lot of scale models, by the way. I built this one with the notion that I really wanted to enter the length of the field or the area that you'd want to set it up. Most of them want you to enter with some kind of craziness, and the math is fairly simple if you look at the spreadsheet, but the only thing you need to do is put a number, and then it's going to compute all the distances. So in other words, Mercury would be about 1 foot. Venus is only going to be 2 feet. The Earth is going to be 3 feet. Mars, 5. You're finally getting out to 17 to 30 with Saturn and Venus, and I scaled it to Neptune. So that's going to be your 100 feet or whatever your number you started with. And of course, an astronomical unit is the distance from the Earth to the Sun. So that's 3.3 feet on this scale model. Now, of course, the actual distance between any two given, you can play games with them. The difference between any two, the maximum distance between this planet and this planet is a lot more than the linear distance, the difference between the distances from the Sun. So you can play some little mathematical things with them. The other thing you could do, by the way, in addition to building this model, you could, the light takes about 8.3 minutes to get to us from the Sun. So you can begin to multiply out how long would it take the light to get to Neptune, for example. It's about a little over 4 hours. So you could do that, and that might be interesting classroom kind of thing. This is a NASA slide. I like NASA things. They have a lot of good resources. But this is kind of interesting because you see how much larger the Sun is with respect to even this massive planet, Jupiter. And of course, Jupiter is much larger than these poor little rocky planets. And then they put Pluto in its right thing. It's a minor planet, along with some of the other new ones. One thing people don't know about is the phases. Your textbooks probably have a picture like that. And it's really a pretty good picture, because there is this progression. You know, the new moon that's dark, because remember, the sunlight's coming from this direction, so the sunlight's illuminating the moon over here, but we see the phases from the Earth. So if you're looking from the Earth to the moon, you're seeing the dark side, which we call a new moon. And if it were perfectly aligned, it would be an eclipse. So as it keeps going, you notice how you get a little bit more light. As it runs around, it gets to a quarter, on these axes. It gets bigger. It's a full moon so all the sunlight's going onto the moon, and so we see the whole face of the moon. This sounds simple, but it's hard for people to visualize it. And of course, this would be a lunar eclipse. There's the same thing. That's a solar eclipse with the bright side of the moon. The dark side is seen by us, and of course it's coming in front. Not everybody gets to see the eclipse. It's only people that are in that shadow, the umbra, or the outside shadow, the penumbra, who would actually see it. The other thing, you can Google this CART-DO seal, and it's a freeware astronomy program. And if you go to the website, you'll find lots of components. So don't just download the basic, download the Hipparchus catalog with it, and download the Milky Way outline and so forth. It's not showing up quite as well as it is on my screen, but you can see the constellation Orion. It's not photorealistic. It is freeware, and it's very accurate, and has a lot of nice features and animation and so forth. If you want a photorealistic one, $100 to $300, and you can zoom right in on the nebula or any of these things, and you'll see lots and lots of detail. I'm not sure it would help you in the classroom, but it might be useful just to have something like this that you could You could pull up, you can look at it. Again, it's like the planetarium thing. You can force it to move around. You can lock on Jupiter, for example, and see the motion of the moons, which is pretty neat. So it's not a bad little thing for free. And the other thing you could do with it is like I've done here, you can use the Clip It feature of Windows or the Snagit programmer. So you can cut it. It's really hard to find little pictures of the constellations, so you could make them this way. And the other little piece of software, it shows you a sky view or a galaxy view. And it's pretty cool because you can click what you want to see and it'll show up in those two views or the sky view.